Hi, here's my first screencast for physics class, and we'll just go through the slides, and you can pause it at any time, and I'll also show you some videos and things in during the slides. Okay, so start by trying these problems, and you should just pause the video now and try these problems, and then I'll show you the solution. Okay, so pause it now. Okay, so the warm-up asked about a wave with a particular frequency traveling at the speed of sound in air, which is around 343 meters per second. And what's the period? What's the wavelength? And the period's 1 over the frequency. And the wavelength is given by V equals F lambda. So one of my students once said you could remember that equation by very furry lambda, but whatever works for you. But then lambda equals V over F, so solve for the wavelength. And then if it's in the same medium, the speed doesn't change. The speed only depends on what medium it's in. So it's in the same medium, same speed. And when a wave travels, for part three, when a wave travels from one medium to another, the thing that doesn't change is its frequency. And you can kind of think about this as if you play a sound underwater or above water and then listen to it underwater, you're going to hear the same pitch. Or if you shine a light, you're going to see the same color, in water or out of water. Or if you think about tapping on a table, the frequency that you're tapping at is the same frequency that's going to go into the air. That frequency doesn't change, and so it's the same 330 hertz. Okay, so just to summarize, the velocity of the wave is determined by the medium, properties of the medium, such as density, um, or if it's a string, tension, mass, things like that will determine the velocity. The frequency and the period of the wave are determined by what's generating the wave, that oscillator. So that's going to be the same even if it goes into another medium. And the wavelength is determined by the velocity and the frequency using that equation, the very furry lambda equation, V equals F lambda. All right, so today I'm going to give you notes on waves and sound, and I'm going to show you a Rubens tube. Okay, so the qualities of waves that we're going to talk about today are um, some of their properties: interference and reflection. We'll talk about diffraction and refraction in a future class. And when we talk about waves, there's so many different kinds of waves and they all behave the same, which is pretty amazing. All right, so today we're going to be talking about interference. And what this means is when there are two waves in the same place, they can add on to each other or they can subtract from each other. And I'll show you a video of this. Okay, this first video is showing reflection. And we have a machine like this in the classroom. I wish I could show it to you in person, but you can see that the wave hits the end and reflects back. Okay, now he's holding the end that it's going to be reflecting off of, and you're going to see it's going to invert. It goes down instead of going up. So when waves reflect off a fixed barrier, like when the end is held, or also if they reflect off a medium that's more dense or more solid, they reflect inverted. Okay, so now I'm going to show you this video of constructive interference or superposition, where two waves are going to come together in the same place right there at the same time. Did you see that? And they build on each other. They add on to each other. They also pass through each other. And while they're passing through each other, they're adding constructively. Okay, one more time. Okay, so just to summarize, constructive interference when they add, destructive interference when they subtract from each other. But it's when they're in the same place. Let's look at some examples of this. So let's say you have these two waves added together in the same place at the same time. They'll add to be, let's say this is amplitude 1, amplitude 1, this is going to be amplitude 2. But if this is amplitude 1 and this one's amplitude -1, the sum is going to be 0. And actually in every place where these two waves are added, if you hold up your ruler here, you'll see -1 plus 1, 0. And even in this location, 0 plus 0 is 0. Any place you add them, they're going to interfere destructively, and so you end up with nothing. And this is the idea behind sound canceling headphones. And I'll show you an example of that with the tone generator in a minute. And if they're slightly shifted from each other, you can actually end up with something of about the same amplitude, not bigger and not smaller. Okay, here I have an online tone generator. I'm going to play 440 Hertz on this one. And I have a second one. I'm going to play 440 Hertz also. Okay, I'm going to stop this one. Start it again. Oh, much quieter. Start it again. Even quieter, it's almost gone. Started it again, now it's louder. So what I'm trying to show you there is that you can have constructive interference, you can have destructive interference, and you can have about the same amplitude or loudness, right? Depending on when you start and stop those tones and how they're interfering with each other. You could try that yourself with that online tone generator. Okay, so this idea of things being out of sync is called a phase shift. All right, so let's look at two waves. One of them's not moving and the other one is moving to the right. And you can see as it moves to the right or to the left, it's either interfering constructively or destructively. There's constructive, there's destructive. And maximally destructive would be 180-degree phase shift. Maximally constructive would be no phase shift. All right, so what if the top one's moving right and the bottom one's moving left? And you can see this kind of thing. But what's so interesting about this is that you notice that the sum of the two waves is not moving right or left. The sum of the two waves is staying in one place. But it's really made up of waves that are moving left and right. And this is the situation we have when we have waves on a string that are going down the string to the right, reflecting off the end and coming back. Meanwhile, more waves are coming in. And the sum of those waves looks like it's not moving at all. It just looks like it's going up and down. We call this a standing wave. It's a vibration where certain points are not moving and other points are moving. So it looks, let's see, what is this? I'll just play this. I don't know. Whatever. It's like the last slide. Okay, here's another little image of this idea of standing waves. Okay. And I think I'll show you a video of this. Oh, there we go. Okay. So you can think about a jump rope or a string. And I'll show you a video of this.
Standing waves are a result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. Sending the pulse at twice the frequency results in the second harmonic. If I triple the frequency, I get the third harmonic.
Okay, so we didn't get to do this in class, but you could try this at home with a jump rope. So if you try this yourself, you'll find that there are only certain frequencies that create standing nodes on on a jump rope or on a, we usually use phone cords, or you could use slinkies. And the frequency that gives you this fundamental, this is called the fundamental or the first harmonic, is there's only one frequency, you know, some rhythmic frequency that will give you that fundamental. And if you double it, you're going to get this one. If you triple the fundamental, you get this one, and you quadruple, you'll get this one. And I'll show you the math for why that is now. So here's the question. Say a slinky has a wave speed, that's the speed the waves are traveling down the slinky, of 24 meters per second, and the total length of it is 3 meters. What wavelengths will give you the first 4 standing waves? Okay, so for the fundamental or the first harmonic, we said the wave speed is 24 meters per second, the length is 3 meters. That means the wavelength is 2 times that. Why? Because the length of the wave, this is actually not a full wavelength. This is a half wavelength. The full wavelength goes up, down, and down, and back to where it started. So this half is missing, and the part we see is half a wavelength. So the wavelength is 2 times that length, or 6 meters. Therefore, the frequency is 4 hertz. Again, we do it again with the second harmonic. And in this case, this is a full wavelength, 3 meters. So the frequency is 8 hertz. Third harmonic, this is actually more than a wavelength, right? The wavelength is this part, or 2/3 of the length. So 2/3 of the length is 2 meters. And the frequency ends up being 12 hertz. And then this is actually 2 wavelengths here, and so the wavelength is the half of the length, or 1.5 meters, and the frequency is 16 hertz. But you can see these multiples. The fundamental is 4 hertz, then the second harmonic is 8 hertz, the third harmonic 12 hertz, and then 16 hertz, and they're all multiples of the first harmonic. Okay, so write a quick explanation in your notes of why will the frequencies between the harmonic frequencies not produce standing waves. Why not? And you can see this if you play some kind of a wind instrument and you try to play at with the wrong amount of let's see how. Well, if you try to play with the wrong amount of force between, try to get the note between like for example, a trumpet has harmonics. Try to get the note between those harmonics, you won't be able to get it. Or if you try to use your jump rope at a frequency in between those frequencies, you won't get standing waves. We're so used to using jump ropes that we find that fundamental frequency when we're using it. So we call those natural fundamental frequencies, or those resonant frequencies, we call them natural frequencies or resonant frequencies, and they depend on the material of the object, the geometry, the ends, whether they're nodes or antinodes. Oh, I forgot to mention about nodes and antinodes. Let's just talk about that for a minute. If we look at this type of problem we looked at before, this fundamental has 2 nodes and an antinode in the middle. Nodes are the places that don't move. So now the second harmonic has 1, 2, 3 nodes, 2 antinodes. Third harmonic has 1, 2, 3, 4 nodes and 3 antinodes. Okay, so that's nodes and antinodes for you. And now I just want to give you some examples of resonance when things find their standing waves or their natural frequencies. That's when you hear a louder sound. And let me show you something. Okay, here's the Tacoma Narrows Bridge, which...
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. During construction, we see the steel girders, 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge.